Welcome back to the deep dive. We are back for part two.
Part two, and we're really getting into the machinery now.
We really are. If you were with us for part one, we spent a lot of time talking about how our own brains lie to us.
Mm-hmm.
We covered the illusion of cause, seeing patterns where there's just noise. We basically made the case that our intuition, it's just not a very good tool for finding the truth.
It really isn't. It's like buggy software. Part one was all about the problem, the diagnosis. You just can't trust your gut on this stuff.
Exactly. But today's about the solution. We're shifting gears from why we get it wrong to how we can actually prove we're right.
We're moving from the psychology to the cold, hard math of inferential statistics.
This is the engine room.
It is.
Yeah.
This is where we stop guessing and we start, calculating. We're continuing our deep dive into these lecture materials from Dr. Beags, and I think we need to be really clear about what's at stake here.
Yeah, lay that out. This isn't just some academic exercise.
No, absolutely not. The concepts we're covering today: null, hypothesis, significance testing, t-tests, p-values. I mean, this is literally the gatekeeper of modern science.
Okay.
If you're a student, yeah, this is that midterm prep stuff that makes people switch majors.
Yeah.
But if you're just anyone trying to make sense of the world, this is the toolkit you need to tell the difference between a real breakthrough and, snake oil.
It's the difference between saying, I think this works, and I have mathematical proof.
Precisely. We're going to try and decode that kind of cryptic language that sometimes feels like it's designed to keep people out.
All right, let's do it. So we're looking at Dr. Beags' course, and the very first big idea, it feels completely backward to me.
It does, doesn't it? It's really counterintuitive.
Because look, if I'm a scientist, right, I've spent a decade developing a new drug for depression. I'm excited. I believe in it. I want to prove it works.
Of course.
But Dr. Beags says my very first step is to assume that I failed.
That's it. That is the cornerstone of the whole thing. It's called the null hypothesis. You'll see it written as H sub 0 or H naught.
H naught.
And the philosophy is you have to start by assuming nothing happened. Your drug is a sugar pill. Your fancy new teaching method is useless. The two groups you're comparing are identical.
So it's like innocent until proven guilty, but for ideas.
That's a great way to put it. Or maybe boring until proven interesting. You have to start with the most skeptical, boring possible version of reality.
Group 1 minus group 2 equals 0. No difference.
That's the null. And the thing you actually believe in, your exciting new drug, that's the alternative hypothesis, or HA.
The backup plan.
Exactly. And you can never prove it directly. The only way you can support your idea is by destroying the null.
You have to prove that the boring version of reality is wrong.
Yes. And there's a 4-step algorithm for it. Step 1, assume the null is true. Assume nothing happened.
Okay.
Step 2, go out and collect your data. Step 3, and this is the magic part, you calculate the probability of getting the data you just collected if the null were actually true.
Whoa, okay, hang on. That's the part that melts my brain every time. We're not calculating the odds that my drug works.
Yep.
We are calculating how weird my results are in a universe where my drug doesn't work.
You've got it. And
Yeah.
to really make that click, the best way is Dr. Beags' coin toss analogy.
Okay, let's do it. I think this is the anchor for everything else.
It absolutely is.
Yeah.
So imagine your friend,
Yeah.
let's call him Dave, wants to flip a coin for money.
Knowing my friends, I'm already suspicious.
And you should be. But scientifically, you have to start with the null hypothesis.
The coin is fair, 50-50.
The coin is fair. That's H naught. Now, we collect data. Dave flips it once. It's heads.
Fine. 50% chance, no big deal.
Flips it again. Heads again.
Feel fine. That's what, a 25% chance? Happens all the time.
Yep. Let's say he flips it 10 times in total. You get 7 heads and 3 tails.
7 out of 10. I mean, it's a little lopsided, but I'm not gonna, accuse him of cheating.
And you'd be right not to. The math shows that the probability of a fair coin giving you a 7-3 split, or something even more extreme, is about 0.17.
So 12%.
Yeah, about 1 out of every 8 or 9 times you did this,
Yeah.
you'd get that result just by dumb luck.
So it's still in the realm of plausible randomness.
Exactly. So statistically, you have to retain the null. You can't reject the idea that the coin is fair. You just don't have the evidence.
Okay, but let's change the scenario. Dave gets cocky. He says, let's flip it 30 times.
Okay, our sample size, our N, is now 30.
And he gets 25 heads and only 5 tails.
Now what's your gut telling you?
My gut is telling me Dave is a cheat and I want my money back.
And why? I mean, what's changed?
Because, well, it just feels impossible. There's no way.
Let's put a number on that feeling. The probability of a fair coin landing on heads 25 out of 30 times is 0.0001.
1 in 10,000.
1 in 10,000. So now you're at a crossroads. You have two possible explanations for what you just saw.
Okay.
Option A. The coin is perfectly fair, and you just witnessed a 1 in 10,000 miracle. Option B. The coin is not fair.
I'm going with B. It's the much simpler explanation.
You are rejecting the null hypothesis.
Yeah.
You're saying this result is so incredibly unlikely to have happened by chance alone that I'm going to conclude something else is going on.
And that's statistical significance.
That is the entire game right there.
Uh,
And that tiny number, the 0.001, that's your p-value.
the infamous p-value.
The most misunderstood, most controversial letter in all of science.
Yeah, Dr. Beags really emphasizes this because apparently almost everyone, including scientists, gets the definition wrong.
They do. It's shocking. If you stop a researcher in the hall and ask what a p-value of 0.05 means, they'll often say something like, oh, it means there's a 95% chance that my theory is correct.
Which is wrong.
It is completely fundamentally wrong. The p-value is the probability of seeing your results, or even more extreme results, assuming the null hypothesis is true.
We're back in that parallel universe. In the world where my coin is fair, how often do I see 25 heads?
Exactly. A low p-value just means, wow, this would be a really rare event in the null universe. A high p-value means, yeah, this kind of thing happens all the time in the null universe.
And there's a specific line in the sand, the alpha level.
Alpha, the magic number. In most of the social and medical sciences, we set our alpha to 0.05.
5%.
5%. If the probability that your result was just luck is less than 5%, so p is less than 0.05.
You reject the null. You declare it statistically significant. You get to publish your paper.
You do, but the question is, why 0.05? Why not 0.01 or 0.06?
It feels totally arbitrary.
Because it is 100% arbitrary. It goes back to the 1920s, to one of the fathers of statistics, Sir Ronald Fisher. He was publishing these tables of values and basically just said, you know what? 1 in 20 seems like a reasonable cutoff, and the whole world just went with it.
So for a century, major decisions about medicine and policy have been based on one guy's hunch.
Pretty much. And Dr. Beags points out how absurd this is. He asks, what is the meaningful real-world difference between a p-value of 0.049 and 0.051?
Practically speaking, nothing. They're the same.
They are. But in academia, 0.049 gets you a promotion and a grant. 0.051 means your study is a failure and gets buried. It's a hard binary where there should be a continuum.
And even if we follow the rule because it's all based on probability, we can still be wrong.
Oh, absolutely.
If my cutoff is 5%, that literally means that 5% of the time I'll see a 1 in 20 fluke, and I'll mistakenly think it's a real effect.
And now you've stumbled into the world of errors. This is where the whole system can go wrong. Dr. Beags outlines the two big ones, type I and type 2.
Okay, let's walk through these. I always get them confused.
Let's do it. So a type I error is a false positive.
The boy who cried wolf.
Perfect analogy. Dr. Beags uses the depression drug example. Let's say a company has a new pill. But in reality, in the true state of the universe, the pill is just chalk. It does nothing. The null is true.
Okay, null is true.
But they run a study. And just by sheer random chance, the 50 people who got the pill happen to have a slightly better week than the 50 who got the placebo.
So the data shows a small difference. The computer spits out a p-value of 0.03.
The researcher looks at that, sees it's less than 0.05, and shouts, Eureka! It's significant, it works. They reject the null. But they are wrong. They've been fooled by randomness.
That's a type I error, and you're saying that if we set our alpha to 5%,
you are explicitly agreeing to be fooled like that 5% of the time. You are building a 5% error rate into the very fabric of science.
that suddenly explains a lot of those wild headlines about coffee curing something one week and causing it the next.
It really does.
Yeah.
It's why a single study means almost nothing. You have to replicate it. The odds of that same fluke happening twice are much, much lower.
Okay, so that's being fooled by randomness. What's the other side of the coin? Type 2.
Type 2 is the false negative. And in some ways, this one is the bigger tragedy. This is when a real effect, a real cure, a real discovery exists in the world.
Mm-hmm.
But your study misses it.
Dr. Beags' example was about peer learning.
Right. Let's assume that in reality, kids genuinely do solve problems better when they work in groups. The effect is real. The null is false.
Okay.
But you run a really poorly designed study. maybe your sample size is tiny, like 10 kids,
Yeah.
or the test you gave them was confusing,
Yeah.
your data is super noisy.
And the result comes back with a p-value of, say, 0.15.
So you look at that and you say, well, it's bigger than 0.05, not significant. You retain the null, you conclude peer learning doesn't work, and you throw the idea away.
When in reality it did, you just failed to find it.
You missed a discovery. And this brings us to one of the most important concepts, which is statistical power.
It sounds like a superpower.
It kind of is. Power is your study's ability to detect an effect if that effect actually exists. It's the probability that you will avoid a type 2 error.
So a low-power study is like trying to find a planet with a pair of binoculars. A high-power study is like using the James Webb Telescope.
Perfect. And if you're a researcher, you want to maximize your power. You want to make sure you don't miss things. And Dr. Beags gives us this trinity of power, 3 main ways to do it.
Okay, what are?
Number 1, the most important one, sample size.
More people.
More people. Bigger is always better. Random noise tends to cancel itself out in large samples. It's why flipping a coin 5,000 times will get you way closer to 50-50 than flipping it just 5 times.
Makes sense. What's number 2?
Effect size. This is about how big the thing you're looking for is. If you're testing a parachute, the effect size, the difference between hitting the ground with one and without one, is enormous. You
Yep.
don't need a big sample size to see that.
Right.
But if you're testing whether a new font improves reading speed by 0.5%, that's a tiny effect. You're going to need a massive high-power study to detect it.
And the third part of the trinity?
It's variability.
Uh-huh.
Or just noise, the messiness in your data. If you have a clean, controlled lab experiment, you have low noise. If you're doing a server on the street in the middle of a parade, you have high noise. The less noise you have, the easier it is to see the signal.
Okay, so this is all the philosophy. Let's get into the actual tools. How do we get from the data to that magic p-value? Dr. Beags introduces the workhorse of statistics, the t-test.
The student's t-test, to be precise.
Right, and I have to ask about the name, students. It sounds like something an undergrad came up with for a class project.
It's actually my favorite story in all of statistics. It was developed by a man named William Seeley Gossett. And he wasn't a professor. He's a chemist and statistician for the Guinness Brewery in Dublin.
Wait, Guinness. The
The
beer?
one and only. Around the turn of the 20th century, Guinness wanted to use science to make their beer more consistent. They were testing different varieties of barley, but you can't run a test on thousands of vats of beer. You have small samples.
Right.
And all the existing statistics worked on huge samples. So Gossett invented a new method, the t-test, to work with small, realistic sample sizes.
So why didn't he call it the Gossett test or the Guinness test?
Because Guinness considered it a trade secret. They didn't want their brewing rivals to know they were using cutting-edge statistical science. So they made him publish it under a pseudonym. He chose student.
That is fantastic. So every Psych 101 student struggling with the t-test is actually using a formula designed to perfect a pint of stout.
That's exactly right.
Okay, but let's get into the logic of it. Dr. Beags says you don't really need to memorize the formula, but you have to understand the idea of the formula.
Yes. Think of the t-statistic as a simple fraction. It's a ratio.
Okay, numerator over denominator.
On the top, in the numerator, you have the signal. That's the difference between your two groups. The deep processing group remembered 4 more words. That's the signal.
Simple enough. A bigger difference means a bigger signal on top.
Exactly. Now on the bottom, the denominator. That's the noise. Technically, it's called the standard error, and it's a measure of the variability or randomness within your groups.
Let's make that more concrete.
Okay, imagine you're comparing 2 classrooms. In classroom A, every single student scored between an 80 and an 85 on a test. They're all clustered together. That's low variability, low noise.
Very consistent.
In classroom B, the average score is the same, but the scores are all over the map. Some kids got 100, some got a 60. That's high variability, high noise.
It's chaotic.
Right. So the t-test divides the signal on top, but the noise on the bottom. If you find a difference between your groups, but the groups themselves are super noisy and chaotic.
The denominator is big.
Right. Which makes your final t-value small.
Yeah.
The test is basically saying, I can't tell if this difference is real or if it's just part of the overall chaos.
But if you find that same difference, and both groups are really consistent and have low noise,
Then the denominator is tiny, and your t-value gets huge. And a huge t-value leads to a tiny p-value. It's the mathematical way of saying this signal is way too strong to be drowned out by the noise.
so the t-test is just a signal-to-noise ratio.
That's all it is.
Okay, and Dr. Beags breaks this down into 2 main types of t-test, independent and paired.
Yes, and this is a huge one for any student listening. You have to know the difference. Independent samples means you are comparing two totally separate, unrelated groups of people.
A group that got a drug versus a different group that got a placebo.
Exactly.
Yeah.
Paired samples, on the other hand, is when you test the same person twice. It's often called a within-subjects design.
Like a pre-test versus a post-test.
That's the classic example. And think about it. Which one do you think is more powerful?
I'm guessing the paired one.
Why?
Because you're getting rid of a lot of the noise, right?
Yeah.
I am very different from you, but I'm very similar to myself from yesterday.
You are your own perfect control group. It reduces so much of that random person-to-person variability, which makes the test much more sensitive to finding a real effect.
That's a great design tip. If you can test people against themselves, you should.
Absolutely. But with the independent tests, there's a little complication, a curveball that Dr. Beags brings up called Levine's test.
Ah, yes. The test where everything is backwards.
Exactly. This trips people up constantly. See, the t-test has some assumptions. It assumes your data is behaving nicely. And one of its main assumptions is called homogeneity of variance.
Which is a fancy way of saying
That the amount of noise, the spread of the scores, is roughly equal in both of your groups.
Okay, so Levine's test is like a pre-flight check. It checks if that assumption is true.
It does. So for Levine's test, the null hypothesis is the variances are equal, which is what you want. You want the data to be boring and well-behaved.
So if Levine's test gives me a significant result, a p-value of, say, 0.01,
That's bad. It means you have to reject the null of equal variances. It means your variances are significantly different. You violated the assumption of the t-test.
so this is the one and only time in statistics where you are literally praying for a big, boring, non-significant p-value.
Yes. You see a p-value of 0.72 on Levine's test, and you breathe a sigh of relief. It means all clear, proceed with the standard t-test.
Okay, I think we need to see an example. Let's walk through the case study that Dr. Beags provides, the deep processing memory experiment.
Yeah, this is a great classic cognitive psychology study.
So set it up for us. What's the experiment?
Okay, we get 40 people to come into the lab.
Yeah.
We want to see if the way you think about a word affects how well you remember it later. We randomly split them into two separate groups, 20 people in each. Group A is our deep processing group. They see a list of words like hammock or school, and for each one, their job is to imagine using that object to survive on a deserted island.
So you're forcing them to think about the meaning of the word, its
Yeah.
function.
Right, you're engaging with the semantics. Now, Group B is the shallow processing group. They see the same list of words, but their job is just to count the vowels in each word.
Hammock. A-O-2. No meaning involved at all. It's just looking at the structure.
It's purely superficial. So both groups go through 50 words like this. Then there's a delay, and then we give them a blank piece of paper and say, write down all the words you can remember.
And the obvious prediction, the alternative hypothesis, is that the deep group is going to remember more words.
That's the prediction. So let's look at the results Dr. Beags got. The deep processing group remembered, on average, 4 more words than the shallow group.
4 words. I mean, is that a lot? Is it a little? I can't really tell just by looking.
You can't. That's why we need the test. So, because these are two separate groups of people, Dr. Beags runs an independent samples t-test,
Okay.
and the computer gives back the results. It says, T with 38 degrees of freedom equals 2.2.
Let's decode that. 38 degrees of freedom is just the sample size minus 2. 40 minus 2.
Correct. And the t-value itself is 2.2. That means the signal, the forward difference, was 2.2 times larger than the background noise in the data.
Which sounds pretty decent.
It is.
Yeah.
And then comes the money shot, the p-value. The p-value is 0.017.
0.017. Okay, so now we compare that to our alpha level, our line in the sand, which is 0.05, and 0.017 is definitely smaller than 0.05.
So what's our conclusion?
We reject the null hypothesis. The result is statistically significant. That forward difference wasn't just a lucky fluke, it's a real effect.
Exactly. Yeah. Just use the t-test to provide mathematical evidence that thinking of the meaning of information leads to better memory than just looking at its surface features.
This is where Dr. Beags adds a huge warning label, and I think it might be the most important part of the whole thing for, real life.
The so what factor.
Mm-hmm.
Statistical significance versus practical significance.
Yes, because we just prove the result is real, but that doesn't necessarily mean it's important.
This is the trap so many people fall into. Remember what we said about power. If your sample size is big enough, You can find a statistically significant result for almost any tiny trivial effect.
He uses the example of a brain training app.
Right. Imagine I create an app and I run a massive study with 5,000 people. That is an incredibly high-power study.
You could find a needle in a haystack with that.
You could. And let's say my app really does improve IQ, but only by half a point, an average of 0.5 points.
Which is completely meaningless in the real world. Nobody would ever notice that difference.
No one. But because my sample size of 5,000 is so huge, the noise, the standard error, is incredibly small. The t-test will come back with a p-value of like 0.04. It's significant.
So you can legally slap scientifically proven to boost intelligence on the box.
You can, and you're not technically lying. It is statistically significant.
Mm-hmm.
But is it practically significant? Is half an IQ point worth $50 a month? Of course not.
So the takeaway for the listener is don't just ask, is it significant? Ask, how big was the effect?
You have to look at the effect size.
Yeah.
And the flip side is also true. Dr. Beags gives the other example. You could have a new therapy that has a massive effect. It helps 40% of people. But if you only test it on 6 people, your study has no power.
And the p-value will come back as like 0.10, not significant.
Right. And you'll mistakenly conclude the therapy doesn't work, when in fact it's amazing you just had a terrible, underpowered study.
It's a real balancing act.
It is. Which leads to sort of the last technical point here, which is about one-tailed versus two-tailed tests.
This always confuses me. It sounds like something out of biology class.
It does. But it's really just about how you place your bet. A normal, standard, honest, scientific test is two-tailed. You're just asking, is there a difference between these groups?
You're open to the possibility that your drug could make people better or it could make them worse.
You are. You're splitting your 5% alpha, your 5% chance of being wrong, into both tails of the distribution. 2.5% on the high end, 2.5 on the low end.
Okay, that seems fair. So what's a one-tailed test?
A one-tailed test is directional. You say beforehand, I am only interested in whether Group A is better than Group B. I don't even care about the possibility that it's worse.
So you're putting all 5% of your alpha, all your eggs, in one basket?
You are. And that makes it easier to get a significant result. It lowers the bar for proof. But it's seen as a bit cheaty. Because what if your drug does have an effect, but it's a negative one? Your test is completely blind to that outcome.
So what's Dr. Beags' advice?
Just stick to two-tailed tests.
Mm-hmm.
Be intellectually honest. Unless you have an incredibly strong, pre-registered theoretical reason to only look in one direction. Just don't do it.
Intellectually honest. I feel like that's a good theme for this entire two-part deep dive.
It really is. Statistics shouldn't be about finding clever ways to get the p-value you want. It should be a system for being honest with yourself about what the data is really telling you.
Okay, before we wrap up, let's give a quick lightning round of tips for any students who are actually using this to prep for a midterm. Dr. Beags had some very practical advice.
Okay, tip 1. Look at the point values on the exam questions. If a question is worth 1 point, it's asking for a definition. Don't write a paragraph. Type I error is a false positive. Full stop. Next question.
Good one. Tip 2. Hunt for keywords.
Yes. The questions are little logic puzzles. If you see the words two separate groups, your brain should immediately go independent t-test. If you see pre-test and post-test, you know it's paired t-test. The words are clues.
And the final one. Don't have a panic attack about the math.
Please don't. The professor knows you're not a calculator. The points are in the interpretation. Do you know what to do when B is less than 0.05?
Reject the null.
And when it's greater than 0.05?
Retain the null.
If you get that part right, you've won half the battle.
What a journey. In part 1, we started with enriched environments helping mice, and now we're here with students' t-test.
It's the journey from I see a pattern to I have proven this pattern is not just random chance.
I want to leave our listeners with one last kind of provocative thought that Dr. Beags mentions at the end.
The replication crisis.
Yeah, that idea. So we've established that if we set our alpha at 0.05, we are knowingly accepting a 5% false positive rate. 1 in every 20 experiments on a useless drug will, by pure luck, look like a success.
Right.
Now, think about the thousands upon thousands of scientific studies that get published every single year. And then remember that journals have a bias. They mostly want to publish the exciting, significant results.
That's the file drawer problem.
Yeah.
All the failures, all the non-significant results, they just get stuffed in a file drawer and never see the light of day. The one lucky fluke gets all the attention.
So it just makes you wonder, in a world that produces this much research, How many of our celebrated breakthroughs are actually just that 5% statistical noise that was bound to happen eventually?
That is the question that should keep every good scientist and every critical consumer of science up at night. And it's why a single study is never, ever the final word.
Science is a conversation, not a declaration.
Well said.
A huge thank you to Dr. Beags for the source material. And to you, thanks for coming along for the deep dive. Good luck on your midterms.
See you next time.